So I think last class was probably the lowest energy class I've ever given. So try to do better today. Find something a bit more exciting to talk about. Well, personally exciting. I have no idea if you'll be as excited about it, but it's a bit more chemistry, which I love because I love chemistry, and I'm trying to find where I hit it. There we go. Okay, so what I want to talk about today is native chemical ligation cyclization. So we've talked about F-MOX-phase peptide synthesis. We talked about strategies for how to make these things. We talked about some protecting group strategies on here. There's not a lot to say. Peptide synthesis is, unlike the carbohydrate stuff, is normally pretty straightforward, except when it's not. And the problem about when it's not is there's no real rules to that, and there's no kind of habits to it. It's just like, oh, that didn't work. I guess I got to try something else. So I don't really see a lot of point in delving into specific one-off details about things. So we're not going to do that. Instead, we're going to probably shift some gears into. Actually, I really hate that terminology. We're not shifting gears because I hate saying it. I just said it twice. We're going to change the angle and talk about some of the post-translational modifications that we can do, or post-synthetic modifications, as I was talking about at the end of the last class. And once we're done with that, I want us to transition into looking at bioconjugation, starting to tie these things together and thinking about how we can go about making more complex constructs from simple molecular building blocks. And we're going to spend quite a bit of time talking about click chemistry and bioconjugation chemistry. So I have it written on top of my grant whiteboard, which I always look at every first thing in the morning, where I have to realize what deadlines are looming over my head now, to put the click chem papers on the web page, which I guess means Blackboard. So I'll make sure that those go up tomorrow. And it's going to be about, I think, 3 or 4 papers. One's going to be the original manifesto review. I love this paper. It was published back in 2002 by Barry Sharpless and his team at Scripps, where they basically laid out the entire concept of click chemistry before it existed. At that point, they must have invented the reaction that's become synonymous with click chemistry, which is the copper azide alkyne cycloaddition. We're going to go into some detail on that reaction, and but they hadn't published it yet, so they knew it was coming. It's actually this really, it's an inspirational review because they knew they were about to blow everything wide open, and yet they're kind of reviewing the state of the field to date. And then it's like, okay, but our stuff coming out is going to be so much better, and we're going to be able to cite this review and say why our technology is so much better. So we're going to discuss that paper. Then we're going to have a couple more recent papers, because 2002 is almost 20 years ago, where we discuss some of the innovations that have come along, especially bioconjugation innovations and in vivo click chemistry. So you can do this inside living cells and inside living organisms, which is just freaking incredible. And this is led by Carolyn Bertozzi. She's now at Stanford, um, who has done absolutely mind blowing chemistry on basically taking chemistry and using the cell as the reactor to do custom chemistry. So we're going to look at Dr. Bertozzi's work and some of the related technologies that are kind of coming out that are trying to do the same thing, trying to do in situ labeling. And we're going to use that as a platform to discuss how we can start putting together molecules, very complex molecules, from these sugar and peptide building blocks. And the reason I want to do that is first, um, theoretically, this is a course on biomaterials. And so this is where the biomaterials come in. It's just we're not talking about cellulose and chitin and boring biomaterials. We're going to be really focusing on sort of the biomaterials, which I think are going to dominate medicine in the future. And that are these chimeric organic molecule peptide sugar things, which are trying to imitate signaling moieties in cells. And we're going to get some really cool biology out of this stuff. I'm super looking forward to seeing where this goes over the next 25 years. Okay, but before we do that, We're talking today about peptides and native chemical ligation and cyclization. And I need to make sure I find my notes because I brought them up somewhere. There we go. Okay. So last class, we finished the class talking about me saying that, okay, well, what we can do is we can switch solvents to NMP and we can really drag that length of that peptide out to 83 amino acids in what I call good yield. For 83 amino acids, pretty freaking incredible. And it's because NMP disrupts these beta sheets. But we can't cheat past a certain point, we get stuck. And sometimes I want something longer than that. So how do I do that? Well, what I can do is I can take my bead and make my peptide, peptide A. And let's say peptide A is 40 amino acids. And I take my bead and I make my second peptide, peptide B. And peptide B can be 40 amino acids. Let's say I make peptide A on Wang resin, which we just saw. I just realized I want to talk about a different resin type here, just to give the other resin. I think about the longest you can generally make on a peptide. I get really, really uncomfortable if we try and make anything above about 35, 40 amino acids. The record is 83, I think. But that's somebody who's a whole lot better at this than me, and it was not their first try. Okay. Peptide B, we're going to make on a resin called rink amide. It's a different resin. I'm just going to talk a little briefly about that. Peptide A, we're going to leave the FMOC on the final amino acid. We don't cleave it. Peptide B, you're going to see why, but we can take the FMOC off. Okay, so when I cleave off Wang resin, we just did this last class, we use TFA. I'm going to get peptide A, an FMOC, and a free carboxylic acid. Now, rink amide, which I always have to pull up the structure of, is still a polystyrene-based bead. It's just the linker is different. Wang had that hydroxymethyl phenol thingy that we talked about, and it was self-immolative, and it fell apart, and it kind of kicked the thing out when you acidified. Rink amide's a little bit different. Just drawing in what this is. The nice thing is it's a little bit better defined generally, so it actually behaves better. You tend to get less garbage coming off a rink amide resin. It's about a lot more expensive, but that's not normally all that important because the price of the resin is not exactly what's hurting your synthesis. Like what's making your stuff expensive is, holy shit, you just stuck 10 amino acids on it. So you kind of want to use the best resin you can.
John, is that a carbon in between the nitrogen and the bead?
Yes.
Okay.
Doesn't technically matter because I guess we could have included that in the bead. Okay, so the thing I want to jump to is we're going to cleave this with acid and water. This is the resin. Remember on the Wang resin, we loaded the C terminus, the carboxylic acid. We're going to do the same thing here. So sorry, I've got this stupid thing here. So on this, what we're going to have is peptide B is attached to this nitrogen. So I'm keeping the resin in red and then peptide B is in blue. So if I treat this with strong acid, what's going to happen is eventually we're going to be able to protonate this alcohol. I want to make sure I do the right one. It's going to be the carboxyl group that's really going to protonate because it's more basic. But no, let's do this right. Do this right. I'll do this right. We're going to protonate that carboxylate or this amide. So I'm just going to draw it in. And this, of course, creates a resonance structure. So I'm just going to focus in on the bottom part of that ring amide. Okay. And it's just the rest of the molecules up there. Now, this carbon here is dibenzylic. It can stabilize a carbocation there reasonably well, and it's going to be really, really good at doing it because if I draw in my double bonds here instead of drawing a circle, we can cleave that to give peptide B plus this. That's a pretty stabilized carbocation there on the left. I've drawn it as an oxocarbenium, but that positive charge is a lot of it's on this carbon here. So this will quite readily want to rearomatize. So any nucleophile present, like water, is going to come in and drive that back. And restore aromaticity. But what we have over here is a weird way to draw an amide bond. It's the tautomer, where we've taken the proton off the nitrogen, stuck it onto the oxygen. It's possible. Doesn't exist like that generally. If there's anything in there that can move that hydrogen around, it's going to. And this guy is going to mostly go and we said we deprotected the other end. So what we have here is rink amide gives acetamides. You know, I'm going to change the color there. And you know what? I'm going to actually write it on a new slide. Hopefully I just didn't erase my entire slide. No, I didn't. Good. Yeah. So this is just, so that functional group is this versus a carboxylic acid, of course, which is this. Now, this is the same thing of like glutamine, glutamic acid. So why is this relevant? Well, now we don't have a carboxylic acid at the C terminus. We don't have that negative charge there. We've got a nitrogen instead. Why is this useful? Well, if we go back to what we just did, what we have is we have peptide A, which has a free carboxylic acid on it, and an FMOC on one side. And now we have peptide B, which is an NH2 and acetamide on there. So if I try and couple these together, I'm not going to get homocoupling. I've protected my carboxylic acid on this one, taking it off the bead. I didn't have to like do some sort of protecting group chemistry after it cleaved from the bead. It just, during its cleavage, it naturally self-protected itself. And so it's very stable. Biologically, it doesn't normally matter what the hell is on your C terminus. It can be one of these. It can be a carboxylic acid. It doesn't normally matter. These guys can be a bit easier to separate because they're not charged on that terminus. But again, 6 of one, half dozen of the other. Where it comes in handy is in a situation like this, where suddenly peptide A can't couple with itself because its nitrogen is protected. Peptide B can't couple with itself because its carboxylic acid side is protected. So if I mix these two together, and I use, HCTU, DIPEA, or I could use DIC and DIPEA, got options. Then peptide A N to C. Yes. If I'm reading this N to C, then peptide B no peptide A is going to be on the N side. FMOC. Peptide B. And I saw a comment flash up. Always use DIC for the humor. Exactly. It is a really good reagent too. There's a like we normally use benzotriazoles for the solid phase peptide synthesis, but in solution phase, the carbodiamides work pretty well. So we can couple the two of them together. And so something what we did is we took a 40 amino acid and a 40 amino acid, and we made an 80 amino acid. Now on paper, this is easy. It's like, yeah, there's one carboxylic acid, one amine, mix them together, it's fine. In reality, this is a freaking nightmare. The yields tend to be low. It's shitty chemistry. I see people report really high yields on this sometimes, and I think they're lying. I think it just doesn't work very, very well at all. And so, because of that, we have something called native chemical ligation. This is exactly what it says on the tin. It is chemical ligation, so attach two things together. And it is native because we are going to take advantage of the amino acid's own chemistry. We're not going to introduce any artificial chemistry. So, this is done by, this is from Peter Kent. He is at Northwestern. He is still an active researcher. He's getting on, but this is, the last, I want to say, the last 15 years that this has been kind of coming into vogue. I think he invented it a little bit before that, but it really has sped up. And we've almost accidentally done native chemical ligation in our lab. We don't want to, but looks like we might do it by accident. So what you do then is you take a look at your peptide. So let's say we have a peptide, and let's say it's 95 amino acids long. No. Let's go 120 amino acids long. At that point, I think I need to make 3 independent 40 amino acid peptides, more or less. 120 is really asking for it. We're getting into like small protein territory here. So how do you go about making something like this? And what he went is, well, something weird happens. And what's weird, I'm actually going to show the example from my group where we almost fucked ourselves because we're morons. Okay, so you've got an amino acid, and it happens to be cysteine. And we thought we were going to be really clever. And we're going to protect the cysteine with these brand new protection groups that we've invented, which are thermally reactive. I'm not going to talk about that because nobody really cares except for me. Okay, but we have a protection group up there. It is a thioester. We got really excited because we can sort of self-immolate these whole protecting groups. We just slowly heat them and they fall off, and it's really selective and it's beautiful and everything works great, mostly. We're going to use these. We're going to just revolutionize the way we make disulfide bonds in solid phase peptide chemistry. And then we hit a problem, which is this native chemical ligation. So you're playing around with your peptide, and let's say you get to this step. So this guy is now attached to the bead, peptide, bead. And your next step is deprotection. PIP for piperidine and DMF. Bye-bye FMOC. Great. All ready to couple the next amino acid. So, you're all very smart people. Can you tell me why this was a stupid fucking idea? We never should have done it. We've solved it. But Peter Kent figured this out. It took him a while, because I think he probably tried to do something similar to what we did and then realized that he had something much cooler going.
You can cyclize there with the amide.
Okay, can you be a little bit more specific?
Like the nitrogen from the amide can attack that carbonyl or the salt, the CO double bond,
Okay, what atom is it going to attack?
the carbon.
Yeah, I agree. So, Paul is smart. Boom. Why is that good? It's a 5-membered ring. Nature loves 5-membered rings more than anything else. We're going to end up cleaving a carbon-sulfur bond and making a carbon-nitrogen bond. That's a damn good trade. Carbon-sulfur bonds are not particularly strong. Carbon-nitrogen bonds are pretty strong. I'm just going to protonate that. Like, we'll grab the proton from somewhere. So what we've done is we've just transferred that ester group onto the nitrogen. Now for us, this is not good because we want to make a peptide. We don't want to transfer that. Thankfully, you do need a bit of heat and a bit of time. And so it's not instantaneous. So we're kind of okay. We also have a workaround that we've developed, and we're very proud of our workaround, and I'm sure something's going to go wrong with that too. But for now, it's great in theory. So Kent's idea was, well, shit. What if I take a look at my peptide? It's 120 amino acids long. There's lots of amino acids along it, and then there's a cysteine. Lots, and there's a cysteine. And let's say it's about 40 AA, 40, 40, 40. That's one more 40 than I need. That cysteine's getting deleted. So what he does, he says, okay, let's find some cysteines that are about a certain distance apart in there. A reasonable distance where I can make the peptide. 40 amino acids seems about good. I can make a 40 amino acid peptide. If you're Peter Kent. If you're me, I start getting really, really nervous at about 25 amino acids. Because I know that bastard's just going to fold over and I'm going to get confused and it's not going to work because everything hates me. But, this is feasible. This is completely reasonable to make 340 amino acid peptides. Then what I do is I build this peptide from C to N, and this peptide from C to N. And on my carboxylic acid side, and this peptide from C to N, I guess I'm going to make it a different color. I should make it blue. Green. So I make the green peptide, and on my CN terminus, I've got an FMOC. Great. And on my C terminus, I've got a carboxylic acid. So now what if I activate that carboxylic acid? Use your favorite activating group. So let's say we use Dick. So we have our diisopropyl carbodiimide intermediate down there. This is, you don't want to go isolating all this. It's not going to be stable, but you can sit around for a few minutes. Then what I do is I add in my blue peptide. And on my blue peptide, you have a carboxylic acid on the other end of the blue peptide. Doesn't matter. Now, DIPA is a weak base. Thiol is a weak acid. So what we're actually going to do is we're actually going to deprotonate that. So the problem with trying to put these together using just peptide chemistry is that NH2 is slow as a nucleophile, but S- is fast. So what we're going to do is we're going to use the S- to attack, cleave, generate my urea. And that takes us to this situation up here. Actually, I guess because I don't have the nitrogen protected, this situation over here. So what we've done is we've used the increased nucleophilicity of an N-terminal cysteine. There's nothing really special about it being N-terminal for its nucleophilicity, but that means the cysteine, the sulfur, is very nucleophilic. it makes the new thioester bond, and that keeps that new and that's a lot easier to make than an amide bond. But that thioester bond is also very weak compared to an amide bond. And we're in close proximity to the nitrogen, and the nitrogen basically transfers it over and regenerates the sulfur as an SH. So what we're relying on here is kind of kinetics followed by thermodynamics. We're relying on the very fast reaction of sulfur with activated carbonyls to make thioesters. And then we're relying on the instability of that thioester in the presence of the ability to be able to make an amide through an intramolecular cyclization. And this is native chemical ligation. It's ridiculously powerful, and it works really, really, really well. And there's really no reason to use anything else if you need to make a long peptide, unless you don't have any cysteines, in which case this ain't going to help you.
Uh, I'm kind of confused how that's any different. Like, why can't, if you go like through the mechanism that you just did, like why can't you cyclize with the amide?
You will. That's
Oh,
exactly what's going to happen, and that's what you want to happen.
oh,
I didn't want it to happen because I didn't have a peptide as my R group.
oh, okay. So that the R isn't a peptide.
Right. In
Gotcha.
my case, the R wasn't a peptide. I didn't want it to happen. And so I like this works whether you have my story or not.
Yeah.
The slide works anyways. But if you want it to happen, this is great.
Okay. Yeah, I thought the R was the peptide. That's why I was
No,
confused.
R is not the peptide in the top one. It was just a protecting group. But now it can be a peptide, and we're going to interrupt and make it a peptide. If it is a peptide, it's exactly what you want to happen, right? Like you want to make a peptide bond. This is ridiculously clever. I applied to go do a postdoc with him just before I got the job here, and he accepted me. So I would have gone off to do that if I. Well, I was going to go to California because I got another acceptance, but this would have been an interesting time. I think I would have learned a lot about peptides because I know just enough to be dangerous. So the problem with native chemical ligations, I said, is you need a cysteine. So what if you don't have a cysteine? And the reason, I'm sorry, I'm just taking a second here because I am looking to try and make sure that I don't skip above stuff. Well, there's a few. Nah, I'm not going to talk about that. It's basically the same thing. We'll talk about this one. There's people who kind of have like clever alternatives to that, but they're basically the same. They still require cysteine, so the yields are slightly higher. This, I think, is the general solution to this whole problem. So let's say you have a peptide with no cysteines in it. So what you need is you want to basically follow the same kind of idea, which is make something more nucleophilic and see if you can get that to work. And this requires, you can do this using either serine or threonine. There are a lot of amino acids, there are a lot of peptides with no cysteines in it. I'm not aware of basically any protein that does not get like lots of serines and threonines in it. They're very, very common. So this, I'm sure there's an example out there of a long peptide of interest that has no serines, threonines, or cysteines, but I'm not aware of it, and I don't think it's ever really been a challenge. So what our general idea here is we want to make So we're going to do some chemistry, but first we'll talk about the overall idea. So we're going to have a peptide. Final amino acid. It's going to be alanine because I just can't be shaded to draw anything else. And what we're going to do is we're going to convert this final amino acid using chemistry I'm not going to cover today. I think it might be one of the assignments to look this up. To a glyoxylate. Glyoxylate-like thing. I guess it's not technically a glyoxylate. And this is a alpha keto acid because it's a acid with a ketone alpha to it. Then we're going to take another peptide. We're building it along. This is going to be the other, you know what, I should draw it on the other terminus just so it's really clear. We have an NH2. We are going to talk about this chemistry because I just want to talk about some synthetic chemistry because it's fun for me. And there's actually a better synthesis that came out since I last taught this course, so that's why I kind of want to talk about that. This is a, you know what, that's a stupid place to draw a bond. Draw that out. Don't do it. Standard coupling. Okay, so that's a little weird, this thing here. This is called, so I'll make sure I have that right. There we go. Five-oxyproline. Makes sense when you think about it. That's proline where we replace an oxygen with a carbon with an oxygen. And now you have this weird oxygen-nitrogen single bond, which just doesn't look natural. So what we're going to do is we treat these two together in a very weak acid. And magic happens. That's just oxalic acid. It's like a double carboxylic acid. It's just a lot weaker than even a normal carboxylic acid. Now, what we're going to have is weird things are going to happen to our poor compound B under these conditions. And some water. Doesn't take much, just a little bit of water. And anytime you see a molecule like this, you got to feel for it, because we were talking a lot about how nitrogen wants to become nitrogen gas. Well, if we put a leaving group on carbon dioxide, it wants to become carbon dioxide. Which is just a bit weird. Funnily enough, this thing will readily protonate up here and not at this carbonyl site down here. I don't fully understand why that happens. There's something happening here. It's a little bit more complex than what we've drawn, obviously. This then is going to react with the oxyproline, and you have a little bit of weak base present, or weak acid, sorry. And we can protonate that nitrogen, which of course puts a delta positive on the oxygen, which is just odd. But negative charge, delta positive on the oxygen. Magic. That's a blue block. And we end up with something that looks like a cheap knockoff of Peter Kent's chemistry. Yeah. Where we have a system like this. If either you take the Bach group off now, or you took the Bach group off before doing all this chemistry, which I probably should have done. I was just going to say A is take the Bach group off. So we'll just protonate this instead. Then we get basically exactly what we just saw with sulfur, except now it's a 6-membered ring. So it's going to be slower. And it's an ester, which is going to be slower. So I lied a bit when I said that we could use serine. It's not serine, it's homoserine. And homo means one extra. So it's got an extra carbon in the. Homo does not mean one extra, of course, but it does in chemistry for no particular reason. A homoalanine means actually means something different than what you think it does, which is really frustrating. Um, so we have this one extra carbon between the OH group and the backbone.
Uh, Sorry, I just had a small question.
Yeah.
The bottom left structure, that nitrogen, that was the one with the block on it, right?
Yes.
So it should have two
Yes,
hydrogens.
it does have two hydrogens.
Okay, just
I'm
just
actually
making.
just going to do it in red so that we can just keep track. Absolutely, Paul. This is kind of cool. Um, like, if your serine is not particularly important in binding to your protein target or anything in there, normally it doesn't matter if you have a homoserine or a serine. You have very similar solubilities, and often peptides have serine included to slightly increase the solubility of the peptide. Uh, like I talk about that, like nature designed it that way. I guess like insoluble peptides precipitate out, so they don't get coded for because they don't do anything useful. Whereas the peptide soluble, it does get coded for because it can stay in solution and do something. So the homoserine and serine are normally pretty much equal trade-offs. Of course, if the serine needs to bind in a very specific way, you're screwed. Don't do this. But this does give us another level of flexibility for doing these kind of native chemical ligations. This is the alpha keto acid hydroxylamine native chemical ligation. So what I want to do is I want to spend a little bit of time actually talking about this guy because I just do. So you're looking at that, and the question, like this whole thing started because I was looking at this a couple of years ago, and I was thinking, how the hell do I make that? And I quickly sketched out that I just make it from homoserine, and turns out that I'm wrong. That's not how you make it at all. So what I'm going to do is I'm going to walk through the synthesis of that material because I want to. It's got a couple of my favorite reagents. So this is just Bach protected hydroxylamine. You know, except for the Bach group, this thing's pretty damn simple. You can buy hydroxylamine, you can Bach protect it, or you can buy it Bach protected, which is easier because it tends to turn into a gas on you when you don't want it to. But when it has a Bach group on, it's pretty stable. And it also already establishes that NO bond. So you get that NO bond by basically taking ammonia and oxidizing it with a really strong oxidant. It's not super trivial to do. I think we actually saw DMDO when we were talking about the carbohydrate chemistry, and DMDO is one of the ways to oxidize ammonia. Anyway, what we're going to do is we're going to protect the oxygen. So this is more an organic chemistry thing, but even organic chemists like using, well, TBS chloride. Love TBS chloride. Okay. Triethylamines acting as a base to sponge up the extra proton. Other than this, mechanistically, The oxygen is attacking. I think we drew this when we were talking about protecting groups and sugars. The oxygen attacks to silicon, then the chlorine leaves. It's an addition elimination reaction. It's not an SN2. Like silicon can make 5 bonds temporarily, which is a little weird. Then we're going to take a weird molecule. It's a proline derivative. But it's got 2 phenyl groups on it. This, of course, at some point came from not a 6-membered ring. That's not possible. Not efficient. Proline itself. And probably double Grignard with phenyl magnesium bromide. It's an ester, so you do a double Grignard. It goes to the ketone, and then it goes all the way down to the alcohol. So what we have here is we have a chiral alcohol, and we're going to protect that. This isn't so interesting. You can buy this reagent. I think when we did silicon protection, we were using imidazole as the major base. For whatever reason, uses triethylamine on top one. I guess it works better for some reason, but they use imidazole here, which is much more normal. Okay. Then we do the main step here, which is combine these things together with something else. So we're going to take nice flat ethyl crotonate. We're going to take our innocent hydroxylamine, and we're going to treat this using good. This. Anyone know what happens? 50% of this is a catalyst. Do it in dichloromethane. Actually, do this in chloroform, but whatever. I know we were talking about this in a class about this time last year, Paul. Okay, bye, Sarah. That's a 2 a.m. family matter. Okay. So what we're going to do is we're going to make an imine. So I'm going to start a new page. And our aldehyde that circle with a slash through is the phenyl ring. is going to attach, and we're going to attach this thing to that. Okay, so like any imine, that's all flat, right? Everything along there is sp2 all the way along there. Like this guy, this guy, this guy, this guy. So I've drawn one product, and everything's in equilibrium. A lot of chiral transition states are hard to get your mind around, but this one, thankfully, is pretty forgiving. So those are the two possibilities. I can flip my nitrogen around. Which one of those two conformation or configurations or stereoisomers do you think is the major component, the major product? Top or the bottom? And why?
Is it the bottom?
Why?
I would just think sterics.
Yes! The answer is always sterics. With these kind of things, when everything's attached the same way, the answer is almost always sterics. Except when it's stereoelectronics. So, that's good. So now let's say, oops, these are all plus charged. Now let's say you're a nucleophile. Out of curiosity, the bottom one's not there. But let's say we had the bottom molecule instead of the top molecule. These two. Which one of these two is more nucleophilic?
Is it the top?
Yeah, do you know why?
Because you have there's a larger difference in electronegativity between the nitrogen and oxygen.
Then between nitrogen and hydrogen?
Uh, Wait, sorry.
You're right, it is the top. So there's something called the alpha effect. And this is heteroatoms attached to heteroatoms are far more nucleophilic than anticipated. I'm being really vague about what causes it because there's a lot of debate over it. I'm firmly in the group of thinking it is purely stereoelectronic effects from the donation of the orbitals on the oxygen into the nitrogen lone pairs space, and so it's much, much more nucleophilic. But there's a lot of people who think that's bullshit, and it's got something to do with electrostatics. I don't quite understand what they're saying. They don't quite understand the stereoelectronic argument. There's problems with both of them. We don't really fully understand the alpha effect, why heteroatoms that are attached to other heteroatoms are much more nucleophilic than we expect. They are. Because heteroatoms are often electron withdrawing, through induction. Like that's how that works. That oxygen is going to pull more electrons from the nitrogen than a hydrogen would. So it's counterintuitive that the top one is more nucleophilic, but it is. So we have a very nucleophilic, and that's really important because if we didn't have that effect, the Bach group is really kind of electron drawing, and so the nitrogen wouldn't be very nucleophilic with just a Bach group on it. But having that OH on it makes it that much more nucleophilic. Anyway, so this guy's coming in, and it's going to do a micro addition, which is that. And I guess the question then is, does it attack the top face or the bottom face of this molecule? I'm going to let Kirsten answer this because I know she's... Or Susanna. Susanna unmuted.
The top face?
Why?
Because the TMSO is on the bottom face.
Yeah, all the big shit's on the bottom, right?
Yeah.
Pure steric argument. This is one of these things where you go, yeah, that makes sense. I understand chiral transition states. And then you pick something harder and you don't understand them anymore. But I like this one because it is super freaking clear.
Dr. Trans,
Yes.
are you not going to address the S-cis versus S-trans issue?
Oh, you left your water bottle in
Oh, you're on Paul's call there. I was like, where the fuck are you?
He's a ghost.
We talked briefly about that up here. I think that's where... Oh, you mean over here? Okay, no, we could, but I'm not going to bother. This is good enough.
There's a very important...
So we can make this kind of system. That's going to then quickly tautomerize back because nothing is unhappier than enolates, enamines. It's going to go back to making this guy. I'm not going to draw in all the other chemistry here. We'll just draw it as a stick. But look at what we've made down there is we've basically made the right stereochemistry for an amino acid. And then we can just hydrolyze that off and regenerate the carbonyl. But now we have an amino acid. We have that homoserine basis there that we want to talk about. We've got that framework. Except we now also have that nitrogen-oxygen bond established. Could you make the nitrogen-oxygen bond on homoserine itself? Yeah, but the yields aren't very good. And that's how people used to do it. And it was really pathetic. These yields, we're talking like 99% for an styrene. It works really, really, really well. And I know it's 99% because it's published in Organic Synthesis. So we have this. But that's not oxoproline. I really want a board because I kind of wander around this way. Okay. So what we do is we take that molecule. I don't like the way they've drawn it. And we want to make the homoserine basis. And so if I want to make homoserine from this, well, the N oxide version, what reagent would you use? It's like beyond the scope of the course, but we can still talk about it.
Could you just use a hydride?
Yeah, which one?
Um, I can't remember what the softest one is.
Well, you don't want the softest, you want the middle one.
Okay.
So sodium borohydride, it won't touch the aldehyde, it won't touch the ester, but it'll reduce the ketone or the aldehyde down to the alcohol. Now, if we remember what we want to do, we want to close this oxygen onto this carbon to make that oxoproline. So what we need to do is we need to remove the TBS group and we need to turn this OH into a leaving group. So we do the second thing by treating it with, they use mesochloride, triethylamine. Just in case. Methane sulfonal is meso. So that's relatively straightforward. And then we need to remove the TBS group. And we got a Bach group. We don't want to remove the Bach group. We just want to remove the TBS group. And so going back to the carbohydrate chemistry part of the course, what would you use to remove a silicon group but not remove the Bach?
Acid?
Yeah, no, acid would take off Bach.
Oh, sorry.
What's the other thing we can use to remove silicon? Fluoride.
Oh, yeah, I just found it.
Okay. Now, we've got that. And you can use, well, it's going to do it spontaneously because, as we were sort of saying, alpha effect, now that OH is next to a nitrogen, is very nucleophilic. 1, 2, 3, 4, 5-membered ring, really good leaving group. Like, there's no other reagent here. It just does this in situ. And then they claim it must work because, again, This is also published in OrgSyn. And the wonderful thing about organic syntheses is it's the one journal you publish in where somebody else actually has to check what you did to make sure that you actually get the yields you say you do. And you're not making shit up. And you get kind of credit for checking it as well as for publishing it. So it's kind of a nice thing. And you make the final product, which is basically that building block for solid phase peptide synthesis, because you have that carboxylic acid, you can attach that, and now you're good to go to do that alpha keto acid hydroxylamine coupling that we were talking about. So all that was just a sort of sidebar talk about this. I just wanted to do some chemistry. Okay, chemistry breaks over. Back to peptides. So we've talked about native chemical ligation, which is this way to make the peptides longer. We're going to talk about non-native chemical ligation next class as part of the click chemistry discussion. But the other big post-translational modification that we're going to see a lot more of, I think, in the next coming years is cyclic peptides. So we're not going to get through this today, but we can get a little bit started. So cyclic peptides are exactly what they say they are. You know, peptides, we've been drawing them so far, N-terminus, C-terminus, peptide. So the problem with peptides is, like, if you're just using them out of the body for something, that's fine. But as soon as you put peptides into your body, and let's say you got this great idea for a drug, and you're like, hey, I got this linear peptide. It's going to make an awesome drug. All my testing shows it's going to work. I inject it into your body. It doesn't tend to work. So, does anyone want to hazard a guess over why peptides are shitty drugs in general?
They're big. I don't know.
No, that's actually not the problem. No, that's okay.
Okay.
Good guess though. Like that is often an issue. As big as a problem, but not for the peptides. They kind of escape all the rules for drug development that you might have learned.
Is it a drug delivery problem?
No, but that's another really good point. Those are two awesome points, but they're not the main issues.
Your turn, Susanna.
Are they unstable?
Yeah,
Or-
there you go. You ran out already.
Oh.
So peptides themselves aren't unstable. You got all these amide bonds. They're really, really stable. But your body is designed to turn them over, right? So peptidases. Enzymes that cleave amide bonds. So there's two main types of peptidases. There's things called exopeptidases. And then there's two types of those. C exopeptidases and N exopeptidases. Now these do basically what you think they might do from the name. Exo means outside. C exopeptidase is a peptidase that chews from the outside of the C side. And so it starts eating, it basically breaks off AAs from C terminus. This does the same thing from the N terminus. These are very, very prevalent in your blood. Again, we were talking about sugars being short-term signalers. Peptides are very short-term signalers. Like a lot of the hormones are peptides, and so like insulin is a peptide. The neurotransmitters tend to be small molecules, but the hormones tend to be peptides. And so they're meant to kind of be pumped out into the blood, taken up by cells, but you don't want them around very long. You don't want cortisol floating around very long. All the sex hormones that, not testosterone, estrogen, those are the core ones, but like a lot of the hormones that initiate ovulation, gonadotropin is a peptide. And the idea is that, you emit these, they have a short half-life, they get broken down quite quickly if they don't get into the right cell. And these are because of you have exopeptidases floating in your blood. You got exopeptidases in the lysosome in the cell, along with all those glycosidases we were talking about. Like they're just basically all processing, recycling factories and just breaking everything down, building things back up. The second class is you have endopeptidases. These break within a protein sequence. Often sequence specific. So often what these will do is they'll look for two specific amino acids being next to each other, or one amino acid away from each other. And they will go and cleave at that point. So you can kind of think it was kind of similar to the restriction enzymes we see in for DNA, for nucleic acids, where they recognize a specific sequence of 4 or 5 nucleic acids. They bind to that site and they cleave there. These are kind of similar. They recognize normally 2 amino acids and cleave between them. They are rarer than the exopeptidases. So one of the ideas is, well, we can evade the exopeptidases if our peptide has no ends. So if there's no C terminus, no N terminus, then the exopeptidase can't get anything to grab hold of. And so that's the benefit of a cyclic peptide. Okay. So basically you'll have your C terminus bound to your N terminus. So I think the last thought I'm going to leave us with for today before we move on, before we end for the day and pick this up again next week, is I want to think about 2 different types of cyclic peptides. Why don't you think about a cyclic peptide with 5 amino acids and a cyclic peptide with 90 amino acids. No, that's a lot. So I get 40. Which is harder to make. So you can look that up. Otherwise, we'll take it up on Tuesday. The other thing that I'm going to do is, as I said, tomorrow I'm going to post, I think, 3 or 4 papers on click chemistry. I'll try and do that first thing in the morning. I'd like to serve. If nothing else, read the 2002. This is relevant because one of the questions on one of the last assignments, and so one of the questions on the final exam, almost guaranteed, is going to involve thinking about how to put together. It's an open-ended question, and it's going to involve thinking about how to put together a complex bioconjugate. And so it's a good idea to have to sort of read about these kinds of things and think about that. And the other thing is, if you end up doing the grad students, okay, the grad students are doing chemistry after their undergrad. Ashley's not here. So Kirsten, if you end up doing chemistry after this course, after your degree, doing stuff, even if you're in biochemistry, if you're doing anything, you're going to run into this click chemistry stuff. It's meant to be the chemistry that's going to be influencing everything. I'm waiting for it to win. And so click chemistry itself won a Nobel Prize a few years ago. I'm waiting for the next thing to win a Nobel Prize, which is the bioorthogonal click chemistry, which is click chemistry that you can do in life, as we were talking about at the beginning of the class. So it's super important because it's completely changing everything we're doing about synthetic biology. And it's kind of bridging that gap between biology and chemistry and allowing us to do chemistry in cells. And it's just really cool. So, and useful. I guess it's useful, but the cool part really gets me interested. So we'll talk about that. There's going to be 3 papers to read. I won't make it 4. That's a lot. I might put 4 in and say read these 3 the other ones for your interest, and maybe it might be useful. And I guess I'll see you guys on Tuesday.
Sorry, John, I just had a quick question. So you said that the keto acid route could give you serine or threonine, and then it actually gives you homoserine. I'm just wondering about threonine. Is it just homothreonine or?
Yeah, I'll be homothreonine for that too. Yeah.
Okay.
Yeah.
Cool.
Yeah.
All right. Thank you.
Yeah. Sorry. Yes. Yeah. Okay.
Thanks, John. See ya.
Okay.
Have a good weekend.